Okay, they don't have a lapel mic for me. So I'm going to talk about a new approach to detecting failures in distributed systems. The problem of failure detection is one that every designer of a distributed system must address either explicitly or implicitly in their design. So for example, in a system with two processes, C and T, process C might want to know whether or not its master T is up. Or C might be some client that's waiting on an RPC request at a server T, and it wants to know if that request will ever be processed. Or C could just be trying to select a server from a server pool, and it wants to ensure the server that it selects is up. The abstraction that answers this question, is process T up, is called a failure detector. Now, typically failure detectors are implemented with end-to-end timeouts. That is, process C considers process T to have crashed if it hasn't heard from T within some fixed period of time. Okay, well, what are the desirable properties that we want out of a failure detector? First and foremost, a failure detector should detect failures, and a failure detector is complete if it eventually detects all the failures in the system. In order to be practical, a failure detector needs to do more than just detect the failures in the system. It needs to detect the failures in the system with enough time for it to be a useful answer to the system. So I'm going to modify this first property just a little bit and say that what we actually want is fast detection time, which is where the failure detector detects failures in the system in a timely fashion. By itself, this property is very easy to get. Just build a failure detector that says every process in the system is crashed. At this point, you don't have a very useful failure detector. So you need to combine this with another property, and that property is accuracy. And a failure detector is accurate if it never says that a process in the system is crashed unless that process is actually crashed. Now, building a system with an inaccurate failure detector can lead to complexity. So going back to this beginning example where we have a backup C and a master T, if C believes the master's crashed, it'll take over and try and become a new master in the system. At this point, without adding extra complexity to the system, you have two nodes that both think they're in charge, and they can run all over each other, causing a muck in your distributed system. So the ideal failure detector combines these two properties, but we aren't going to get them for free, so we really want it at a low cost. So I'm going to define an ideal failure detector to be one that is simultaneously fast and accurate and unobtrusive. By unobtrusive, I mean the failure detector should have low cost in terms of system resources and shouldn't disrupt the system too much. Unfortunately, unpredictable latency means that there's a trade-off when designing a failure detector. The failure detector can use a long timeout or a short timeout. If the failure detector uses a long timeout, it's giving up on fast detection time. If it uses a short timeout, well, then the failure detector will time out even if the remote process is up. And you can deal with this in two ways. The failure detector can pass the buck on to the application, giving up on this accuracy property, or it can back up its answers with remote kill, terminating the timed out process. In this case, the failure detector will be killing processes that are actually up, which will disrupt the operation of the system. And note that as you make the timeout shorter and shorter, it's more likely that the failure detector will say something is down when it's actually up, or kill a correct process. Now, what we found is that just building an end-to-end failure detector gives up too much in this trade-off. Indeed, we were able to build a failure detector called Falcon that is simultaneously fast, accurate, and unobtrusive. Falcon has sub-second detection time. This is 1 to 2 orders of magnitude faster than existing approaches using timeouts. And this directly translates into a decrease in the period of unavailability following a failure, which we saw when we integrated Falcon with Zookeeper, a cluster management service. But getting speed by itself is nothing. You need speed plus accuracy. Falcon is also accurate. And it gets its accuracy by terminating some components of the system. And this is a technique that we borrow from high availability clusters, including Linux HA. And accuracy has the benefit of allowing you to design simpler applications. No longer do you need to worry about two guys thinking they're boss in the system because the failure detector will only say that a node is crashed if it's actually crashed. But getting both of these is going to come at some cost. And my claim is that Falcon's costs are low enough that it's an unobtrusive failure detector. So when Falcon kills, it does so surgically, a technique that we borrow from Micro Reboot. And Falcon is able to avoid false suspicions just because a node is temporarily unresponsive end to end. That is, Falcon can avoid mistaking the symptom, unresponsiveness, for the disease, which is a crash failure. And Falcon is also low cost in terms of system resources, using only a small amount of CPU. given the state of failure detection today, how are we going to get around this trade-off that I told you about and build a failure detector that can simultaneously achieve all three of these properties? Well, it starts with this observation, and that's that using an end-to-end timeout is based on this abstraction of a process. But underneath the abstraction, T is actually a complex system composed of many layers. And we hypothesize that a failure detector that uses the information available in these layers can simultaneously be fast, accurate, and unobtrusive. Okay, what kind of information am I talking about? Well, in the application, there's some indication as to whether or not the application is doing its job. If it's a SQL server, it should be processing SQL queries, or maybe more generally, if it's running some event-based library, the event loop should be running. But there's also information available in other layers. For instance, in the operating system layer, the failure detector can ask the question, is the SQL server in the process table? To test this hypothesis that using this information can lead to a better failure detector, we built Falcon. And the rest of my talk is divided into two parts. First, I'm going to tell you how we built Falcon, and then I'm going to tell you how well Falcon works. To design Falcon, we began with a set of principles. And the first principle is to gather inside information. And this is the layer-specific information that I've just given you an idea of what we're going to get. Now, sometimes this information may involve a timeout implicitly. So say the failure detector wants to know if some counter like Jiffy's is being incremented. In order to say, well, Jiffy's isn't being incremented, the failure detector needs to say if Jiffy's hasn't been incremented within the last 100 milliseconds, it's never going to be incremented again. And we favor local timeouts instead of end-to-end timeouts because a local timeout only needs to reason about the layer that it's observing rather than the end-to-end behavior of the system and can afford shorter timeouts as a result. Now, in order to achieve accuracy, Falcon may sometimes need to use lethal force to terminate layers that it has just timed out on. But in order to be unobtrusive, Falcon needs to ensure that it uses lethal force both sparingly and surgically. To build Falcon, we needed to pick a target environment, and the environment that we chose is a data center that uses virtualization. And I'd like to emphasize that virtualization is something that we take advantage of in our implementation, but it's not fundamental to the approach that I'm going to describe. Okay, so we're going to deploy these software modules called spies to monitor the different layers of the system. So you have, a spy monitoring the application, a spy monitoring the OS, and a spy monitoring the hypervisor. And I'm going to describe this system by answering three questions, starting with, okay, well, what exactly are these spies doing? So spies are in two components. They occupy two layers of the system. We call the top layer the monitored layer, and the layer below that the enclosing layer. And there's a piece of software for the spy in each of these layers. Spies are sent out with a mission. They're there to gather inside information about the monitored layer from both the monitored layer and the enclosing layer about whether or not the monitored layer is up. And they're also allowed to use lethal force. That is, they're deployed with a license to kill. Now, I'm going to take a step away from this high-level description for a second into the specific implementation of two of our spies. And I'm going to start by explaining what the application spy does. So, as I said earlier, there's some indication as to whether an application is doing its job. So, the application spy that's monitoring a web server will ask a question like, is the web server processing HTTP requests? But the component in the operating system will ask the operating system about the web server. Is the web server in the process table? And if the spy needs to use lethal force to terminate the application, it relies on operating system signals to do so. Now let's take a look at the operating system spy. The operating system spy has a component in the operating system, and in order to determine whether the operating system is alive or not, the spy asks the question, is the operating system scheduling processes? Now there's also a component in the hypervisor layer that's monitoring the operating system, and in order for it to determine whether or not the hypervisor or the operating system is up, it asks the question, is the virtual machine that's running that operating system alive? And if the OS spy needs to terminate that operating system, it relies on the hypervisor to terminate the virtual machine. Okay, so I've described two of the spies in the system. We have a third spy that monitors the hypervisor, but I'm not going to get into those details right now. You can check it out in the paper. I'm going to go back to describing the system by answering the second question. Okay, we've got all these spies in the system. They're gathering inside information, but I told you that there's going to be this failure detector thing. How do we combine all this stuff and get a failure detector? And what we do is we put in the client this client library, and the client library uses the spies to provide the abstraction of a failure detector. And it does so with a very simple answer. The spy needs to answer the question, is process X crashed? And it does so by saying yes, process is crashed, if any of the spies say that their layer is gone. Otherwise, it says that no, the layer is the process is alive. Now, this gives us an accurate failure detector for two reasons. First, spies are able to see whether or not a layer is alive locally. And second, lower layers enclose higher layers. That is, it's necessarily true that all of the applications running on an operating system have crashed if that operating system has crashed. Falcon gets its fast detection time from the combination of inside information gathered by the spies and callbacks. Inside information means that in the common case, spies will see a failure shortly after it happens and then immediately call back to the client library, which can give a fast answer to the client. Okay, well, this is what happens in the common case, and the next question that you're probably wondering is, well, what are the corner cases of this design? And perhaps the most obvious one is, well, the spies are also some process that's out there. What happens if they crash? Well, we've designed the system in such a way that lower layer spies are going to monitor higher layer spies. And it might seem like we need to develop some sort of inter-spy communication protocol for the spies to realize what's going on with each other. But it turns out that the design of this system allows spies to monitor each other implicitly. So the operating system spy can monitor the application spy by watching the operating system. If the operating system crashes, then the application spy crashes. And so the operating system spy can watch it that way. Well, okay, there's other ways that the application spy can crash than if the operating system crashes. What if it crashes, but the operating system is up? Well, that means that the application spy can't detect failures. And so that's a subset of this second corner case that I'm going to talk about when a spy doesn't detect a failure in the system. In this case, the only entity in the system that knows there's a problem is the client C. And in order to keep C from waiting forever and to provide Falcon with better coverage, we're going to fall back to a large end-to-end timeout backed by a remote kill. Now, this is acceptable for two reasons. First, we don't use this end-to-end timeout in the common case, so we can afford a long timeout. And second, because we're using a long timeout, it's less likely that Falcon will terminate a process that is actually up. Our third corner case is when the spies in the client library can't communicate because of a network partition. In order to have accuracy in a failure detector, something has to confirm that the remote process has crashed. If there's no communication between that something that's confirming that the remote process has crashed, in our case spies, and the failure detector, there's no way to give an accurate answer. Since Falcon is designed to give an accurate answer, it must wait until the partition is healed before it can give that answer. Okay, I've told you how we built Falcon by answering these three questions and telling you about some of our spies. Now I'm going to move on to the third part of my talk, where I tell you exactly, how well does this work. But before I can do that, I need to tell you some specific details of our setup. So we deploy Falcon across 4 layers of the system. As you saw, we have the application layer, OS layer, hypervisor layer, and network. And we inject 8 synthetic failures into the system to measure how well Falcon responds to those failures. And in order to compare with existing approaches, we use a third-party library of timeout-based failure detectors. So I said that we want our failure detector to have 3 properties. We want it to be fast, accurate, and unobtrusive. And I'm going to go through each of these properties in turn and how Falcon uses them and how they can benefit a distributed system. But keep in mind that as I'm doing it, any one of these properties by itself is easy to get. It's getting the combination of the 3 that's the challenge. So Falcon has sub-second detection time of failures. And to measure this, what we did is we took this system that I showed you earlier. We have a process C and we have a process T. And we inject a failure at process T, in this case, kernel error, and we see how long it takes C to detect that failure. And we do this 200 times, and what I have here on the y-axis is the median detection time, and the error bars that I'm showing are the first and 90th percentile. And I'm comparing Falcon with 2 other end-to-end timeout-based failure detectors. One is just a fixed ping, heartbeat-based failure detector, and the other one is an adaptive end-to-end timeout, the Berthier failure detector. And as you can see, Falcon detects this failure much quicker than the end-to-end timeout approaches. And that's because of the combination of inside information and callbacks that Falcon uses. Now, this has the direct benefit of reducing the period of unavailability following a crash. We saw this by injecting the same failure at a zookeeper leader and a zookeeper cluster. We have a single client that's querying the cluster in a closed loop. And what we want to measure is okay, we inject this failure, what is the longest period of unavailability that the client sees? And what we found is that when Zookeeper used Falcon as its underlying failure detection mechanism, there was a lower period of unavailability than when Zookeeper was using a end-to-end timeout-based approach. Okay, so that's fast detection time, but as I said, it's easy to get fast detection time by itself. Falcon is also accurate, and Falcon gets its accuracy from these two assumptions in the system. The first assumption is that the spies can confirm that a layer has crashed. And that is, just locally it can see that its layer is gone. The second assumption is this assumption of an enclosing property. If the operating system crashes, all of the applications on top of that operating system have also crashed. And this directly translates into the ability to design simpler applications, which we saw when we used Falcon to build a simple state machine replication library. So state machine replication takes this idea of just a single server and replicates it so that there's this abstraction of a single correct state machine. And typically this is done, and in this, well, not typically, but in this library that we used, it has a proxy, a primary, and several replicas. And so what we were able to do is we were able to reduce the code complexity by about 21%. And I'm going to give you an intuition of where exactly we had savings in this 300 lines by giving you just one example. So in building a system where you have a primary and a set of replicas, the replicas are going to need to have some protocol to start a leader election to take over when the primary crashes. Using an accurate failure detector means that the leader is never going to see a leader election request, because if a leader election request occurs, it's because it's dead. But if the system is using an inaccurate failure detector, the primary needs to be ready for a coup d'etat. It needs to be ready for the replicas to rise up with a leader election request and take over. So this is just one of the ways that we were able to reduce the complexity in this design of a state machine replication library. Now, getting both of these benefits is going to come at some cost. And I'm going to tell you about the costs of Falcon, which are the costs of using lethal force and a failure detector and the actual system resources that we use. So when Falcon kills, it does so surgically. And so for all 8 of the failures, when Falcon killed, it killed the smallest possible component. So if there are multiple apps running on the same OS, it didn't need to kill the entire operating system to kill the faulty app. And for 2 of the failures, Falcon actually didn't need to use lethal force. And that's because the spies were able to monitor the layers and say, oh, okay, this thing is gone, we don't need to kill it. The second aspect of Falcon is how Falcon responds to load in the system, or sort of these temporary conditions where the target appears to have failed, but hasn't actually crashed. So to do this, we injected a whole bunch of different kinds of temporary load into the system. And what we found is that for most of these, Falcon correctly held its fire. But for 2 of them, Falcon did terminate the application when it was under load. And the reason for this is that the spies were unable to locally distinguish between failure and the condition, the temporary condition. We also measured the resource usage of Falcon, and in this case, we were interested in, okay, we're running these spies that are doing monitoring. That's going to use up CPU. What kind of CPU usage do we get? And so we just monitor the components of the spies at each layer of the system, and this is what we found. So the spies don't use too much CPU to get this fast and accurate detection time. So combining this low CPU usage with Falcon's approach to killing, we get a failure detector that is simultaneously fast, accurate, and unobtrusive. Now that I've told you why we built Falcon and how we built it and how well it works, I'm going to move on to some discussion about Falcon. And I'm going to start by telling you how we plan on addressing some of the limitations of the current implementation and other future work we have planned. So right now, Falcon is designed for a very specific stack, and that appears in 2 ways. One, we have an operating system spy, and that operating system spy watches Linux. We'd like to diversify and have an operating system spy that also watches Windows and other operating systems. But there's also the composition of the layers that Falcon assumes. So we'd like to look at removing the virtualization from the system and potentially adding other layers such as application-level virtualization in something like the Java virtual machine. Second, Falcon has spies. These spies know what's going on in the system. why should the failure detector give a binary up-down answer if it can provide more information? This information can be useful for faster recovery in the system. We're also looking at combining Falcon with existing approaches such as Gossip to build a scalable monitoring service when in-nodes need to monitor each other, leading to n-squared monitoring pairs. I'm going to talk about some related work very quickly. There's been work done on the theory of failure detection. There's also been work done to show that you can build a fast and accurate failure detector if you have specialized hardware. There's also been work done on making end-to-end timeouts better by making them adaptive and changing their interface with an accrual interface. We borrow the techniques of killing for accuracy, fine-grained information, and killing surgically from outside work where they were used independently or singularly. And there's also been work done in building distributed system services that can act as failure detectors in a system. But these systems don't provide the accuracy guarantees that Falcon does. And underneath it all, they're really just using end-to-end timeouts to determine whether or not other nodes in the system have failed. So at the beginning of this talk, I told you that there's this trade-off. You have to give up fast detection time, accuracy, or unobtrusiveness. And I said that we were going to get around that trade-off, but that was a bit disingenuous. What we're actually doing is we're moving this trade-off to a different layer of the system. We're making this trade-off a local trade-off. And by doing this, we're able to pay less disruption for the speed and accuracy benefit that we want out of a failure detector. So Falcon is designed to combine a number of new and existing techniques with a novel architecture to present a failure detector that is simultaneously fast, accurate, and unobtrusive. By detecting failures in the distributed systems with the Falcon SPI network, we hope that you can build distributed systems that are more responsive for the end user and easier to design with the developer. I'm ready for questions.
So do you think that some of the components that you're monitoring are more reliable than others, and some of the nodes you're monitoring might be more reliable than others? Or are you operating in a world where every node is homogeneous, every component is homogeneous?
So I understand your question to have two parts. One is that these entire composed layers is one more reliable than the other, and then the other portion of your question is, do we treat any layer as more reliable than the other?
Fine.
Okay, so we don't treat any layer as more reliable than any other. Falcon treats each of the layers identically in terms of how it's monitoring. So the decision as to whether or not something is more reliable depends on the questions that the SPI is asking. You could imagine asking more lenient questions of a layer that you're expecting to not fail too often, and more strict questions, and having tighter guarantees on a layer you do expect to fail.
So do you think that's a realistic assumption, that everybody is just as likely as everybody else to fail?
I'm sorry, I didn't hear the first word in that question.
Do you think that's a realistic assumption, that every component you're monitoring is just as likely as every other component?
I don't know that that's necessarily an assumption that we're making.
Didn't you just say you'd make
I said you could make that assumption by adjusting the questions. Like, you could use that assumption to gain the questions, but I don't think that there's anything fundamental in treating this node as likely to fail as this node in Falcon's approach, because it's looking at this local information.
Okay.
Robert Van Renesse, Cornell University. So I like this work a lot, and I'm excited that you'll be using my work in future versions of this. However, I was surprised to see that you applied it to Zookeeper.
Mm-hmm.
Like Zookeeper, it uses an asynchronous consensus protocol, and so, for example, when the say the NIC of the leader breaks or the cable comes out or whatever, Zookeeper can go on. But as I understand it from your approach, when the cable comes out, everything will just stop. Is that right?
Can you repeat the end of your question?
So because you're using accurate failure detector to detect the failure of the leader, and you don't have a mechanism to detect the failure of the leader when the network cable comes out, the Zookeeper will come to an abrupt halt when, in fact, the original system could just merely go on.
So it's actually the hypervisor SPI that will detect the particular failure that you've described.
How would it detect it?
It monitors the interaction that it has. So there's a component running on the switch that's connected to the machine, and it says, this machine is not responding to pings, and then cuts off that machine from the network and says, this machine is dead.
But the machine isn't dead.
But it's cut off from the network, which is equivalent to dead. for the sake, well, for our particular approach. So if the machine was on some sort of shared disk, then no, that wouldn't be. You need some additional fencing mechanism to take care of. But for the sake of this, it's cut off from the network and isolated, and that's what we're treating as crashed.
Okay, well, let's talk about this more offline.
Okay.
Paulo Verissimo from the University of Lisbon. Yeah, Robert, you almost stole my question. I mean, so let me try to generalize Robert's point. Inaccuracy from detectors comes from asynchrony.
Okay.
And so I like your ideas a lot, but maybe something that has to come out clearer is how do we insert synchronism, not only in the local detection mechanisms, because it's not enough to say that you have something embedded in an operating system. If the operating system doesn't have real-time features, for example, you cannot do synchronous things. And the networking issue is perhaps a more important one. If the network is not synchronous, which it isn't, it's going to be difficult to say that you have an improved accuracy of the detector full stop, because it will always be hampered by errors in the detection mechanism of the network. This is Robert's problem.
So one thing that I think you're getting at is this idea that the application, there's some timeout within the application, and you're measuring that timeout, and that's using real time in the operating system, and you may run into an issue when there's a lot of load in the operating system. What we do there is, instead of measuring that time that's local within that operating system as a function of real time, we measure the actual CPU time allocated to that application.
Oh, but I buy that.
Okay.
I buy that. Even if you weren't that clear, I know that you can solve that locally. But I'm more worried about the network, because the network is essentially asynchronous, right? So if you don't have, say, for example, an alternative control network about which you can make more synchronous assumptions, if you lived on what Ethernet locally and Internet gives you, you're going to have that problem, because the Internet, that network will behave asynchronously, and essentially you cannot tell slow or partitioned hosts from failed hosts, right? I'm just asking, that's my... Inaccuracy derives from that, you understand. So I didn't understand how you can claim... part of the accuracy will be local. I buy it.
Okay.
It's neat. I like it. But part of the inaccuracy is given by the network, and so for that you don't have control unless you have an architecture or you have a dual network or something like that.
So the third corner case that I talked about was this network partition, and what we say is that because communication is required between these components for accuracy, in the case of this network partition, Falcon's going to have to wait.
Okay. Or an alternative, if you're in a data center, use an alternative network that keeps you connectivity for the signals, the Zyma-Live signals. Okay, thank you.
Hi, Mark Curini, Harvard University. Thanks for that presentation. I'm wondering, can you detect conditions like live lock and maintain liveness properties? What if you have a situation where you have like multiple applications communicating in the same OS, and they're making forward progress, but they're consuming more resources than they're really designed to or supposed to, or
so that's
due to a memory leak, for example?
That's actually a very interesting question. We do have a mechanism for determining live lock within the application, which is that the spy asks this application-specific question, so it can say, oh, is this application live locked? But live lock amongst a group of applications is actually something very interesting that I haven't thought about before that I think we're going to look at in the future. So thank you for that question.
It's time for one more.
So seems you need to install this spice, Dingyuan from UCSD and your UC. So seems you need to install the spice in every layer in your software stack. So do you assume developers do it manually for each software stack, or you need to have some automatic ways to do it?
So this is, do you need to design a new spy for each layer that you're integrating with? So we talk in the paper about some ways to generalize the spy's architecture. So for instance, to build a new spy for the application, all you need to do is provide a function that answers the question, is the application doing what it's supposed to do? And that's the layer at which we sort of have like the best way to generalize the spy to alternate layers, but it's definitely future work to look at using that type of technique to sort of get this, any OS able spy.
Quick question, Rodrigo?
Rodrigo Rodriguez from MPI. Congratulations on a good talk. Just a low-level question regarding your evaluation. when you compared against the timeout-based detector, what value did you pick for the timeout? How did you choose it?
So we chose a value for the timeout based on what we had seen in related work, which was generally on the order of tens of seconds. And so we picked a timeout of 5 seconds to try and be sort of aggressive with that.
Okay, just a quick suggestion. You could have been more conservative by choosing a timeout that had future knowledge of sort of what's the highest latency that you would observe in the future. And I bet you would have still looked good even though you were using a very conservative value.
Okay. We'll look into that for future. Thank you.
Okay, thank you.